So the first thing is tonight is we got homework 7. This is for Tuesday. I believe we're getting ready to change months. I picked one problem out of chapter 12. That was one of the problems I wanted to assign last week. This is the one where you're going to use a normal distribution. You're going to use a continuous probability model to find probability. And then I picked 3 problems out of this chapter 13. I picked 13.31, 13.41, and 1353. Now, I told you there was 3 things I wanted to talk about out of this chapter 13. This one here is going to require a Venn diagram. And then once you see a Venn diagram, once you can make the Venn diagram, you can answer whatever the question is. This one here is about a two-way table. And we're going to calculate probabilities from a two-way table. And this one here is going to use a tree diagram. Now, there's no graphs here. Normally when I write stuff, I'm looking for something out of Minitab. No, I'm just telling you what you're going to use to solve these 3 problems. Because when I go through this chapter 13, I'm going to work a problem where you make a Venn diagram and we answer questions based off of it. I'm going to look at a two-way table and we're going to calculate probabilities from it. And then I'm going to have a problem where I got to make this tree diagram, this picture of what's going on, and then we're going to calculate from probabilities from there. So tonight I'm going to do a problem very, very similar to each one of these. The Venn diagram, the two-way table, and the tree diagram. Okay? Actually, we're just changing the setup. They're the same problems. So I wanted to do that because those are the 3 things I'm going to talk about. Now, the other thing is this. Test 2. It's going to be on Thursday, the 5th. That's next Thursday. It's going to be over chapters 6, 8, 9, 12, 13, and 15. So that takes the two-way table. That's your sampling. That's your experiments. 12 and 13 is probability. And 15 is something called a sampling distribution that we're going to work on the end of tonight and on Tuesday. Now, what I've done is this. I know I'm a little bit early, but since the test is going to be on Thursday next week, at 7 o'clock tonight, you're going to see my thoughts for test 2. So what I've done is I went through each chapter, told you what you need to be looking at, what you need to think about. I've actually given you some problems to reference on, okay, you need to be able to do this. Look at this problem. This is the kind of problem we're looking at here. That problem's not going to be on your test, but it's going to be that style of problem. All right? So, like I said, and then I've actually done a couple things where I've given you some page numbers. The 2 that comes to my mind is you need to know the definition of a simple random sample out of Chapter 8, and you needed to know the 3 principles of experimental design out of Chapter 9. Hell, I gave you the page numbers on my thoughts. Go there, look, know those. All right? This will show up in D2L, and it's under content, if I remember right, syllabus. If I didn't know any better, I'd say the thoughts for test 2 are right under the thoughts for test 1. Okay? And again, it's all the homework solutions are there. The one for the one you're going to get back today, right? Homework 6 from Tuesday. That solution will show up at 7. I know that the problems I just gave you here, you're not going to get those back before the test. But I'll post solutions next Tuesday, maybe at 11:30, to give everybody a chance to get them to me, so you'll have all your solutions there. You may not have all your grades, but you'll have all the solutions. The test is going to look like the other tests. 40 questions, multiple choice, A, B, C, and D. Right? I just go through my thoughts and start finding questions that match. That's the way it goes. The streamers, I'm going to send you an email later tonight and reminding you about what options you got, or I'm going to assume you're going to use the same option you did last time. Obviously, you people in Sam Wilson will be there. You folks here will be here. The streamers will still be going to Wharf Pickle 517 where you went the last time on Thursday. I'll send you an email before I leave tonight, okay? So that's where we're at. Now, what I want to do with the rest of this chapter 13, all right? Again, I'm not going to go through and like I do page by page here. One of the things I want to remind you is the last thing I wrote up on Tuesday. One thing is we talked about two events being disjoint, right? They're disjoint if they don't have any outcomes in common. There's no overlap. There's no outcome that's in A and it's in B, right? So there's nothing there in the middle of that Venn diagram. And if that's the case and you want the probability of A or B, it's the probability of A plus the probability, right? If they're disjoint, you add. Hell, that's one of the rules we know. The other one I talked about was two events being independent, right? Meaning if you know A occurs, that doesn't change the probability that B occurs, right? Where you do A and then you do B. Yeah? The last thing I wrote up was if you've got two events, two independent events, and you're interested in the probability of A and B. Anytime you see that and, you're worried about independence, on how do you calculate that probability. If they're independent, nothing to worry about. You just multiply. All right? Now, what I want to look at here is I want to look at a problem about a Venn diagram. I wanted that out there for you. I'm going to use that on you here in a minute. This idea of two events are independent, then the probability of A and B is the probability of A times the probability of B. And I'm going to underline that word. If they're disjoint, you're interested in or, you added them. All right? So where I'm at is, I'm on page 307, and excuse me, even further than that. I'm on page 309 here. And I want to look at a little problem on page 309. The problem I want to look at is problem 13.5. What you're going to see me do is I'm going to pick problems out of your homework problems here to do. Because, I mean, you can look at the examples. In this 13.5, they're talking about college degrees. It says, of all college degrees awarded in the United States, 50% are bachelor's. I always try to write the information down as we go. It says 59% are earned by women. Okay. It also says 29% are bachelor's degrees earned by women. Now, in this language, I've got 29% that are bachelor's and are earned by women. I like that and part. That's the overlap. These are the ones that are in both. These are bachelor's degrees and they are earned by women. Okay? It says, make a Venn diagram and use it to answer these following questions. So remember, when you start a Venn diagram, that big rectangle, that represents your sample space. That represents all the degrees earned. Okay? Now, I'm not going to use A and B on you. I'm going to use B for the bachelors and W for the women. That's how I'm going to label my events here. And there is overlap. These are not disjoint. Here is going to be my bachelors, and here is going to be my women. Okay? Now, there's 4 spots that need to be filled in, and I'm going to number them for you. There's a 1, 2, 3, and the outside's 4. When you got a Venn diagram that has 2 events, and there's overlap, there's outcomes in common, there are 4 spots to be filled in here. If I can, I always try to start with the number. I labeled that one in the middle there number 1. That's the overlap. These are the outcomes that are in common. In this case, this is the ones where they are bachelor's degrees and they are earned by women. Okay? So here's where my 29% is going to go, is right here. I know on Tuesday I was counting cards for you and I put the cards in there. I don't know how many degrees go in there, but I know 29% of them were bachelor's degrees and they were earned by women. That's the reason I put the 29% there. Right? You tell me how many degrees are earned and I'll tell you how many go in there. I'm going to take 29% of them. You don't tell me that, I'm going to put the 29% there. All right? Now, you see number 2? Number 2, I got to do this. I might regret this, but this part right here, that number 1, that is bachelors and women. That's B and W, right? That's both. Those are the ones in common. This part out here, this number 2 that I have, this is B and not W. So they're bachelor's degrees, but there's bachelor's degrees and they are not earned by women. That's what that little number 2 is. Well, if 59% are earned by women and 29% of the, if 50% are bachelor's degree and 29% of them are earned by women, how many are bachelor's degrees that are not earned by women? That's got to be your 50 minus your 29 there. This has to be your 21%. How did I get that? That is 50 minus 29. Pay attention. Number 1 and number 2, those are all the bachelor's degrees. There's 21%, there's 29%. You add those together, you get your 50 that was given to you in the problem. This is what the Venn diagram is doing for us. It's stopping from you counting those 29% twice. Okay? Now, you see number 3 over here? These are the ones that are women and they're not bachelors. Right? So the degrees earned by women, the catch is they're not bachelor's degrees. Well, how many were earned by women to start with? 59%. You've already got 29% there, so this has to be 30%. What did I do? I took 59 minus 29. Now, if you'll notice, if you'll look at the ones I have labeled 1 and 3, there's 29% in 1, there's 30% in 3, 29 and 30 is my 59% that are earned by women. Now, how are we going to find the 4th one? Well, what is the 4th one in language? The 4th one is this outside here, right? These are not bachelors and not women. So these are all the degrees other than bachelor's that are earned by men. How am I going to find that number? Well, you're going to take 100 minus 21 minus 29 minus 30, and then what the hell does that give me? %. You see the 4 numbers that's in your Venn diagram? 21, 29, 30, and 20. What do they add to? They add to 100%. Why do they have to add to 100%? Because every degree shows up somewhere in this Venn diagram. That has to be 100% of them. Okay? Now look, I don't care what questions they ask me. My focus is can we fill this out? Okay? Now, you'll notice all these things I have written in blue. I was just trying to give you the language, right? The number 1 is women and bachelor's degrees. Number 2 is bachelor's degrees are not women. Number 3 is women and not bachelor's degree. And then number 4 is they're not bachelor's degrees and they are not women. I'm just trying to give you the language of what fits in what little part there in 1, 2, 3, or 4. All right? Now, do you understand why I hesitated? I'm looking at people just to see how much I can get away with here. Like, how much do you want me to tell you at this point, or how much can I tell and everybody doesn't fall out of their chair? This is probability, right? This is the language. This and, right? This and that, or not this means it's not that, right? Okay? Now, while I'm here, I got to say one more thing. I've said everything I can say about and. If I take 1, 2, and 3, those 3 pieces, right? Forget 4 for a second. What is the language I use for those three? 1, the middle, 2 over here, and 3 over here. That is A or B. Go back to Tuesday where I did the problem with the cards. I was looking at kings and I was looking at red cards. And I want to know how many were kings or red cards. I added those three numbers together. 2 plus 2 plus 24. That's how I got that 28 on Tuesday. Is that correct? We did that problem. That is the or part. Right? Anytime somebody's looking at a Venn diagram and they're asking you about A or B, it's always the one in the middle and the 2 on the outside there. We missed the fourth one. That's not an or. It's either A or B. So it can be in A, or it can be in B, or it can be in both. All right? The Venn diagram stops you from counting those ones in the middle there twice. That's what it does. Now, so whatever kind of question they ask me, it says, A, what percent of all degrees are earned by men? Okay, no problem. I got to be able to see the Venn diagram. What areas are we talking about, the ones earned by men? Now, I'm going to make a big deal out of this, but surely the God you understand, if 59% are earned by women, then 41% are earned by men. What are we talking about here in the Venn diagram? Which ones are earned by men? It's number 2. I'm just picking out what am I looking at here. It's 2 and 4. Well, what is that? It's 21 plus 20, which is where that 41% comes from. There's no shock. Shit, if 59% were earned by women, all the rest of them were earned by men. 100% minus 59 is 41. What are you adding in the Venn diagram? I'm adding 2 and 4. The 21 plus the 20. Right? Part B says, what percent of all degrees or bachelor's degrees earned by men? Where are we looking? Where are the bachelor's degrees that are earned by men? Do everybody see number 2 there? And I'm talking about the area number 2. Those are the bachelor's degrees, and they are not women. Well, if they're not women, what are they? Those are men, right? So for that one right there, I'm just looking at that spot that's 2. There's nothing to be done here. It's just 21%. Okay? That's it. I mean, hell, I could ask you what percentage of the degrees are earned by women and they're not bachelor's degrees. I'm talking about spot number 3 here, right? What percentage of the degrees are earned by men and are not bachelor's degrees? That's the 4, right? Those are the ones that are not bachelor's and they're not women, they're men. There's a bunch of questions once you have the Venn diagram sitting in front of you that somebody can ask you about it. But you notice what I'm doing. I'm just picking out which little areas or which little area is the area that I need, and I'm just writing down the percentage there. That's all I'm doing. Okay? Now, don't freak out if some problem with the Venn diagram gives you the probability that you fell in there. If I give you a probability, am I giving you a percentage? Move the decimal place to the right. I'm looking at a percentage. Here, we're giving you percentages. How do I turn this into a probability question? Well, we choose 1 degree recipient at random, and I start asking, what's the probability that they're a man? Looks to me like it's 0.41 because 41% of them are men, right? I choose 1 at random. What's the probability that it's a bachelor's degree earned by a man? Well, that's number 2 there, right? A bachelor's degree earned by men, that probability is 0.21. Whether they're asking you about percentages or whether they're asking you about probability. You remember on Tuesday, how did I change the normal distribution problems to probability questions? We chose 1 at random. That's what we're doing here. If you want to turn these into probability questions, choose a degree recipient at random. Now, what's the probability the person you chose is a man? Hell, it's 41%. It's 0.41. Choose a degree recipient at random. What's the probability that it's a bachelor's degree and it's earned by man? Oh, it's 21%. It's 0.21. Same problem. If I can calculate the percentages, I can tell you the probability. All right? Now, Part C says this. And I'm not going to be as near as loud and obnoxious about C as I am A and B. But there is a question in your homework where you're making a Venn diagram that looks like this Part C. And Part C wants to know, are the events earning a bachelor's degree and being a man, independent. So, bachelor's and being a man. The question is, independent. So here's the way we attack this problem. What's the probability, what's the percentage that is a bachelor's degree? What's the percentage that are bachelors? What was it? 50% are bachelor's degrees, right? I went all the way to the top. I didn't even, if you want to look at the Venn diagram, it's 2 and 1, 21 and 29. The percentage that are bachelor's degree is 50%. What percentage are men? That's my 41%. What is the percentage that are bachelors and they're earned by men? We just figured that. That was part B. That was 21%. Right? I'm reading everything off the Venn diagram. The percentage that were bachelors was 50%. The percentage that are men is 41%. That was part A. The percentage that are bachelors are men, that's part B. That's the 21%. Now, if these things are independent, I'm going right back here. If they're independent, it's at the top of the page. The probability of A and B, the probability of a bachelor's and a man, is supposed to equal the product of those two. Well, what we need to look at is, what do we get when we take the percentage bachelors times the percentage that is? Now, we need to turn this into decimals. Okay, what do I get? Like 0.205 or something? Which is 20.5%. If these things are independent, that product is supposed to equal the and part. The and part is 21%. The product is 20.5. This ain't no round-off error. If they're independent, this should be exact. So the deal is, they're not independent. Because the probability of a bachelor's and a male does not equal the probability of a bachelor's times the probability of a male. If they're independent of each other, that product would equal. They don't equal. They are not independent. Now, I'm way more concerned with you folks about parts A and B than I am part C. All right? Way more concerned. I want to get that out there to you. Hell, we talked about what it means to be independent. We're using that definition. It turns out they're not equal to each other. Hell, these two events aren't independent. And like I said, 13.31, the one that you're going to do for homework that's got a Venn diagram, there's a part A, there's a part B, and part C asks you about these two events being independent. That's what you want to do. You want to check what's the probability of each one of them, what's the probability of the B and M, and then check the product. If they are equal, and I mean equal exact. I understand that 21% is close to 20.5%. Close ain't good here. Should be equal to. One should be 21, the other one should be 21. If one's 20.5, the other one should be 20.5. Right? They got to be equal. No round off. There's not a problem here. Okay? That's my Venn diagram problem. The one you're going to do for homework, 1331, it's a Venn diagram problem. How do I know that? I'm telling you, you're going to want to use a Venn diagram there. How's that? The problem didn't tell you. I'm telling you to do it. It's not about bachelors and women and stuff like that. Yours is about 1331 is about tendon surgery. You have a torn tendon, and we are facing surgery and are facing surgery to repair it. The surgeon explains risk to you Infection occurs in 3% of such operations. The repair fails in 14% of operations, and both infection and failure occur together in 1%. So, you're going to let the infection be I, that's one of your events, and that happens 3% of the time. You're going to let failure be a capital F in your Venn diagram, and that happens 14% of the time. And the overlap, infection, and failure, that happens 1% of the time. That's the part that goes in the middle there. Okay? Make a Venn diagram. One event is infection, the other event is failure. 1% goes in the middle, and then you can fill out the other ones. I had to look really hard in your homeworks to find one where they gave you the one in the middle. When I give you a problem next Thursday using a Venn diagram, I'll give you the one in the middle because we work from the middle out, right? Just like the problem I did it in class here. Now, that's our problems with Venn diagrams. The next type of problem I want to be able to do, all right? Now, our book labeled these as conditional probability. Does anybody remember conditional distributions from Chapter 6? You know, where we fixed a row, we fixed a column, and then we looked at the distribution of the other variable? Well, we're looking at a conditional probability. Anybody know why I put given that in parentheses? That's the same language I used on you when you were looking at conditional distributions. That's going to be the same language I'm going to use on you when I'm looking at conditional probability. Look, I'm thinking about probabilities from a two-way table. And it's just not conditional probability. That's one of them that shows up in a two-way table. Now, what I want to do is this. I'm not going to look at any of this other crazy stuff here. I'm going to come over to your homework, and I'd like to look on page 322. Okay? And the problem I want to look at is, I want to look at problem 13.39. What I want is I want a two-way table, and I want to tell you how I can calculate whatever probability somebody's asking me based off your two-way table. As a reminder, a two-way table, that's two categorical variables. One's the row, one's the column, and we classify everybody by the two categorical variables, right? It says, a striking trend in higher education is that more women than men reach each level of attainment. The National Center for Educational Statistics provides projections for the number of degrees earned, classified by level and by the degree, the sex of degree recipient. Here are the projected numbers of earned degrees in thousands in the United States for 2015-2016 academic year. Your row variable here is their gender. The column variable there is the type of degree. The row variable has two possible outcomes, female or male. The type of degree is either associate's, bachelor's, master's, or doctorate. Everybody see that? That's a two-way table from Chapter 6. All right? It tells me how many people are in this table. It looks like 3825. Yes, I know that's 3,825,000 because they chopped 3 zeros off every number in this table. They've summed the rows for you. They've summed the column. And then in the lower right-hand corner, they've given you the table total. Those 3 zeros means nothing to us that they chopped off. It's told in the problem that these are in thousands, right? So there's 3 zeros at the end. I'm going to use 3825 as my table total. Now, before I get to any problems, in Chapter 6, I would have gave you this table, and I would have asked you, what percentage in this table are males, and what would you have done for me? You'd have took the number of males, 1569, and you would divide it by the total number of individuals in this table, 3825. Correct? Wouldn't that be what you did? Look, we did all kinds of those in Chapter 6. Or if I'd have looked at this table in Chapter 6 and said, Okay, what percentage of the degree recipients earned a bachelor's degree? What would have you done? You'd have took the number of bachelor's degree, which is 1869, you'd have divided by 3825, and you'd have gave me the percentage that had a bachelor's degree in the table. Yes? You'd have gave me little percentages out of the marginal distributions if you want it like that. Back in Chapter 6, I could have asked you, what percentage are bachelor's degree given that the person we're looking at is a male? Is that a conditional distribution? Given that they are a male. You're only looking at the males. How many out of the males had a bachelor's degree? That's 803 divided by 1569. And you would have gave me that as a one piece out of that conditional distribution, right? And that would have been the conditional distribution of degree level given that the person is a male. Anybody wonder why I'm bringing up Chapter 6? When you had a two-way table in Chapter 6, all you did was calculate percentages. I already warned you, anywhere you can calculate a percentage, you can calculate a probability. So how do I turn this two-way table into questions about probability? Choose a degree recipient at random. Now the questions are about probability. Okay, you chose a degree recipient at random. Now what's the probability they're a male? What's the probability they have a bachelor's degree? What's the probability they got a bachelor's degree if I know the person is a male? The hell, that's the same three questions I just gave you out of Chapter 6. Now, just while we're here, if I've got 3,825,000 degree recipients, remember there's 3 zeros there, and if I choose one of them at random, what does your sample space look like? Is any one of those 3,825,000 possible? Yeah, that's your sample space, right? Any one of these 3,825,000 people that are represented in this table is a possible outcome when you choose one at random. Your sample space is everybody in the table here. Okay? So then what kind of questions can we answer here? Well, you look at Part A. I put this choose a degree recipient at random on top because all the problems have that. Part A. It says, if you choose a degree recipient at random, what is the probability the person you chose is a man? Okay, I want to know what's the probability that you chose a man. How many men are in the table? 1569. How many people are in the table total? 3825. Anybody got a calculator? 0.4. So when you choose one at random, the probability you choose a male is 0.41. What's the percentage of males in this table? The hell, it's 41%. Right there it is. It's the same calculation. Okay. Now I got to add to Part A. Could I have asked you for what's the probability you chose a female? Yeah. You'd have took 2256 divided by 3825. You know what you got as an answer? 0.59. Okay, let's choose another one at random. What's the probability you choose somebody that has a master's degree? How many people in this table, how many degree recipients actually earned a master's degree? It's 816. There's 3825 people in the table. What'd you get, bud? 0.21. So if you choose a degree recipient at random, what's the probability you chose someone that got a master's degree? The probability is 0.21. Let me ask you this. What percentage of these degree recipients earned a master's degree? It's 21%, right? It's the same calculation. Now, you understand there's 1, 2, 3, 4, 5, 6. There's 6 questions I could ask like this, right? 1 for each row, 1 for each column. Yeah. Those are parts of your marginal distribution out of Chapter 6. Okay, then we go to Part B. It says, what is the conditional probability? Now, when I ask you questions, I don't give you that part. I'm going to ask you, what's the probability that you chose a man, given that the person chosen received a master's degree. What's the probability that you chose a man? Now, here's math people using symbols. Given that, yeah, the line stands for given that, a master's. Math people are lazy. Anytime I can trade two words in for a line, I'll go for it. When you see that notation, we're looking at a conditional probability here, right? The probability of a man, given that the person that you chose has a master's degree. You know something about the person you chose. You know they have a master's degree. Now look, I never said this about conditional distributions. When I'm thinking about conditional probability, what it does is you're not looking at everybody in your sample space now. It cuts your sample space down. You know something about this person you chose. You know this person has a master's degree. The reason I make a big deal out of that is because what number goes in the denominator? It's not everybody in the table. It's only the ones that have a master's degree. 816 of them. Okay? And then out of those 816, how many are males? How many are men? 322. For a probability of 0.39. The given, that's the key. When people talk to you, well, if anybody else was talking to you about conditional probability, what they should tell you is, what conditional probability does for you is it cuts your sample space down. You're not looking at everyone or everything in your sample space. You're only looking at a part of it because you know something about the person or the object that you chose. We know the person here earned a master's degree. I'm only looking at the ones that earned a master's degree. That's the reason for 816 in the denominator. And then, what am I thinking? Out of that group, out of the group that have a master's degree, how many of them are men? There's 322 of them. That gives me a probability of 0.39. Is there a bunch of questions I could ask you about conditional probability? Yeah. Suppose I want to know the probability of a woman, given that they have a doctorate. Now, I read the symbols the same way the question be worded. You choose a degree recipient at random. What's the probability that you chose a woman given that the person has a doctorate degree? So you're not looking at everybody. The given that is telling you who to look at to start with. You're only looking at the ones with the doctorate. How many have a doctorate here? What is that, 182? This is going to be 182. Those are the ones with a doctorate degree. Out of that group, now you're not looking at everybody in the table again, you're only looking at that column of doctorate degree. Out of the doctorates, how many are women? That's the 95. And this gives me a probability of 0.4, 0.52. Oh yeah, a little bit bigger. Now, it don't always have to be given that the degree. What's the probability that the person earned a, let's do this one, a master's, given that they are a man? Now, the reason I'm doing that one, you see the ones at the top of the page? That's the probability you got a man, given that that was a master's degree. Now I flip-flop, right? Now I want the probability you got a master's degree, and what I know about the one you chose is that they are a man. How many men are in this table? What is that, 1569? Out of the 1569 males, how many of them have a master's degree? 322 for a probability of? Exact? I have a reason for asking for exact. So there's a whole bunch of conditional probabilities I can calculate here. The given that part is telling you what group you're looking at. That's the number that goes in the denominator. And then the part before that is you look out of that group, how many were males or how many were females or how many had a master's degree. That's how I'm getting the number that's in the numerator there. Now, we need to look at part C because it looks just like the one I did with the Venn diagram. Part C wants to know, right? Are the events choose a man and choose a master's degree recipient independent? So a man and a master's. The question is, are they independent? Now I could do that. The probability of a man and a master's, is that equal to the probability of a master's? I could do what I did with the Venn diagram. But here's the thing. What was the probability of a man? That was the first problem we did. What did we get? 0.41? Is that right? What was the probability of a man knowing that the person had a master's? Is that 0.39? Is that true? We already calculated those. Let me go back up the page here. The probability of a man was 0.41. The probability of a man with a master's is 0.39. So here's the question. Did the probability of a man change once we know that the person had a master's degree? Remember, that's what independent is, right? Knowing that A occurs doesn't change the probability of B occurring, right? So now, in the second one there, we know it have a master's degree. And now we want to know what's the probability of a man. Well, it's only 0.39. When I didn't know anything, right, it was 0.41. You see how these two do not equal each other? That means they are not independent. Because the probability of a man does not equal the probability of a man given that the person had a master's. If they were independent, those two things would be equal. Because you would have the same probability of getting a man even if the person did have a master's. It wouldn't change the probability. It changes it. When you know the person has a master's degree, it changed the probability of getting a man. It went from 0.41 when you didn't know shit to 0.39 when you knew the person got a master's degree. Rob, I'm in the corner. I mean, I don't mind looking at the corner, but I kind of like to see the students better. Thank you. Okay? Now, why am I using this on you? Because now we know a little bit about conditional probability. That's what that is. You know, when you have the probability of a man given that a master's degree, that's the probability of B occurring knowing that A has occurred. Right? If it doesn't change, then those two should be equal. I'm not done talking about this one yet. I'm going to write the little formula down here about, okay, so what the hell is the formula here, right? Independent. I'm not done with my two-way table. Means the probability of B is equal to the probability of B given that A occurs. Go back and look at my definition I wrote down last week. Oh, yeah. In words. If we know that A occurs, that doesn't change the probability of B occurring. It's exactly that. The probability of B is equal to the probability of B given that A occurred. Yeah, remember I warned you on Tuesday about how many things I'd write down for you? As far as formulas and stuff like that? I'm just trying to make sense of what the hell I just wrote above there. Now, I'm going to add like a part D and a part E to your two-way table here. All right? So, part D is this. You still choose one at random. Still choosing one at random. I got probability questions. Now I want to know what's the probability that you get a man and they have a master's. Now you notice, you didn't hear any given that shit come out of my mouth. What I want to know is, you chose one at random. I want to know the probability that you chose a man and that person has a master's degree. I want to know that they have these two characteristics out of your variables. That it's a male and they have a master's degree. You didn't cut the sample space down with and. You're still looking at everybody in the table. So you're still looking at 38, 25. Then the question is, out of everybody in this table, how many of them are males and they have a bachelor's degree? Well, you find the males, you find the bachelor's degree, and you're going to find males' bachelor's degree is 803. Is that correct? For a probability, or if you like, a probability of 803 divided by 3825. So the probability that you choose a person, a degree recipient at random, and they are male and they have a master's degree is 0.209. Let's do another one. What's the probability you choose a woman and they have a doctorate? No conditional. I want to know that they have these two characteristics. That's what the and is, right? They're a woman and they have a doctorate degree. This should be 3825. How many are women and have a doctorate degree here? 95. Ooh, that's a small probability. What you got?
0.025.
Very small. So, I mean, there's a bunch of and questions, too. Now, I'm going to scream at you about this. Yeah, I know, it's Thursday night, hell, Halloween's on Saturday. You don't want to hear me scream, but I'm going to scream at you. When you see and, this one, this and that, the number in the denominator is everybody in the table. The number in the numerator is out of the body of the table where it's this one, and I read across, and that's how I'm picking out 95 or the 803. All right? Now, there's a part E. The probability of a man or so in part D, the important word was and. In part E, the probability of a man or a master's, the important word there is or. Now, they don't have to have both. They got to be a man or they got to have a master's or they can have both. Right? Now, here's the thing. I'm going to stay away from the ugly formula that shows me exactly what I want to do here. What I want to do is this. You still didn't cut anything down. You're still looking at everybody in the table, so your denominator is still 3825. So then my question is, out of this table, how many of these are males? Is that 1569? How many have a master's degree? 816? Now, did we count anybody twice? Yeah, we did. What did we count twice? We counted the ones that were twice that had males and master's degree. We counted the ones twice that is 322. Everybody see where I'm reading? Because if you think about it, when I added up to get the males, 322 was in there. When I added up to get the master's degree, 322 is in there. You can't add them in there twice, right? So you have to subtract. Okay? Anytime you're dealing with a two-way table and it's an or like that, see, these things aren't disjoint. This idea of a man and master's degree, they're not disjoint. Whatever that problem... Did you get a number for me?
Yeah,
0.54. Let's do one more of these. Right? Let's say we choose one at random. I want to know what's the probability you get a woman or they have a doctorate. Again, no conditional. I want this event or this one. How many are women in this table? 2256. How many have a doctorate? 182. And again, the problem is they're not disjoint. You counted things twice. How many did you count twice? Well, you counted the ones that were women and had a doctorate degree twice. You counted 95 of them twice. Probability? So I'm going to do this to you. With the or, remember, if they were disjoint, you'd have just added them up, right? In a two-way table, they're not disjoint. There's something overlap, right? There's people in the two-way table, there's objects in your two-way table that will have both characteristics. Well, you counted them when you went this way, and you counted them when you went this way. You've got to subtract them out once. You can't count them twice, right? So, same thing here. These are not disjoint. How in the hell do I know? When I look at the man in master's degree, well, hell, there's 322 of them that are males, and they have a master's degree. In the Venn diagram, that little part in the middle there goes 322. Right? I don't want to go all the way back there to you, but that part in the overlap of the males in the master's degree, that'll have 322 in there. Yeah? I'm not going to make the Venn diagram for you. I'm just going to tell you, look, you know you count them twice, subtract them out. Now, that's every probability question I can think of for a two-way table. Just straightforward, that part A we did, conditional probabilities. Part C, the thing about being independent. Part D, the and part, right? You're just plucking one out there. And then the or part, a part where you added them both, and then you subtract out the ones that were counted twice. That's all of them. Okay? Surely that'll take care of the problem I gave you for homework. Now, the third thing. Look, a Venn diagram's a tool. It keeps track of stuff for me. The two-way table, that's just another thing I can calculate probabilities from. The third thing is a tree diagram. Okay? Now, again, I'm not going to get carried away with what the book's doing there. What it does for me, to me, I treat the tree diagram like the Venn diagram. It helps keep track of probabilities. Now, the reason I say we need help here is there is more than one step. You're going to do this, and then you're going to do the next thing. And then, hell, I don't know, we might do a third thing. All right? Now, I'm sure the book must have a problem that they've done here. Yeah, that's example 1310. I'm going to look at this problem on page 316. I wanted something where we started from scratch and it wasn't all written out for us so I can show you how it works. So I'm on page 316. And I want to look at problem 13.13. Okay? It says PSA screening for prostate cancer. The prostate-specific antigen PSA test is a simple blood test to screen for prostate cancer. It has been used in men for over 50 years as a routine part of a physical exam with levels above 4 Ng per milliliter indicating possible prostate cancer. The test results is not always correct, sometimes indicating prostate cancer when it is not present, often missing prostate cancer when that is present. In other words, you get false positives and false negatives here. That's what they're talking about. Here are the approximate conditional probabilities of a positive above 4 and a negative test result given cancer is present or cancer is absent. They give it to me in a table. Now, these are conditional probabilities. It says the rows are the cancer is present, the cancer is absent. The columns are the test result is positive or negative. So you see that 0.21? That is the probability of a positive test given that cancer is present. You see that 0.94? That is the probability of a negative test given that the cancer is absent. It does a better job when the cancer is absent, doesn't it? You understand why I'm saying that? Well, hell, when this cancer is absent, you'd expect the test to come back. It comes back with a probability of 0.94. It don't do too good when the cancer's there. Right? You would expect if the cancer's present, positive only comes back with 0.21. That ain't worth a crap. Okay? that's neither here nor there. That's just me looking at I didn't really look at the numbers before, and I'm thinking, that test they need to come up with something else. That ain't very good. It does good when the cancer's not there, but when the cancer's there, it don't do so damn good. Now, it says, in a large study of prostate cancer screening, it was found that about 6.3% of the population had prostate cancer. Question, if 6.3% of the population has prostate cancer, what percentage of the population doesn't? That's everybody that's left over. That's 93.7%. Agreed? Okay. It says, draw a tree diagram for selecting a person from the population. Outcomes are the cancer's present, cancer's absent, and testing the blood. Outcomes, test comes back positive, test comes back negative. See, you're doing more than one step. So, we're going to choose a person at random. The cancer's either present or absent. Agreed? That's the first step. And then, no matter which way it is, you're going to test their blood, right? And so the test will either come back positive or negative here, or the test will come back positive or negative there. Okay? Now, the thing about a tree diagram, it's a tree on its side. You follow the branches to find out the outcome in your sample space. So when I follow this upper branch, I get the cancer is present, the test comes back positive. The cancer is present, the test comes back negative. The cancer is absent, positive test, absent, negative test. This right here, that right there, those four outcomes, that's your sample space. That's your S. Those are the four possible things can happen when we do these two steps. Choose a person, test their blood. Now, we got to figure out probabilities here. Well, if I choose a person at random from here, what's the probability I choose somebody that has the cancer present? Well, if 6.3% of the population has the cancer present, then the probability of getting somebody that has the cancer present is, again, if 6.3% of the population has the cancer and you choose one at random, the probability you get a person that has the cancer is that 6.3%, 0.063. What's the probability you chose somebody that didn't have it? Well, if 6.3% have it, what is it? 93.7% don't. Probability is 0.937. Now, the other ones, look, we put the probabilities on the branches going out to the outcomes. That's the way the tree diagram works. Now, you see I got four more probabilities to fill in. How do I know that? There's four more branches there. Now, what's the probability that the test comes back positive given that the person has cancer? That's the table. The test comes back positive. The person has cancer. That's the 0.21. Does anybody know what the next branch down needs to be? You ain't even got to look at the table. They got to add to 1, right? Just like the 0.063, 0.937 adds to 1, because one of those two things has to happen. Here, either the test is positive or negative. If that's 0.21, I don't need the rest of the table. Hell, that's 0.79. Now, on the bottom there, the cancer is absent. Well, what's the probability of the test coming back positive when the cancer, given that the cancer is absent? That's the table. The test comes back positive. The cancer is absent is 0.06. What's the next line? I don't need the table. It's got to add to 1. This has got to be 0.94. Now, the way you come up with the probabilities in your sample space when you're using a tree diagram, you multiply the probabilities on the branches that make your outcome up. In other words, this one here would be 0.063 times 0.21. This would be 0.063 times 0.79. I'm multiplying the probabilities on the branches that make up my outcome in the sample space. 0.937, 0.06, 0.937, 0.94. Now I have a question. If I pulled a calculator out and I multiplied all those things together, and if I added these up, what are these going to add to? Anybody? If I added all those together, they're going to add to, how do I know that? You got 4 outcomes in your sample space. Those 4 probabilities better add to 1, right? That's one of the little things about being a valid probability model. Now, we did all that work to answer part B. What is the probability that the test is positive for a randomly chosen person from this population? Well, I need part B. The probability that the test is positive. It happens in 2 places. It can be that the cancer is present, the test is positive. Cancer is absent, the test is positive. There's 2 places you can get a positive test. Does anybody know why I'm adding? Are those outcomes disjoint? Those outcomes are disjoint, right? That's the reason I'm adding. So you take the numbers, and whatever we get here, what is this? 0.063, 0.21, plus 0.937, 0.06. This turns out to be 0.01323 plus 0.05622 for a probability of 0.06945. That's the probability that your test comes back positive, irregardless of whether the cancer is absent or present. I couldn't do this in my head. There's no way. There's no way I could keep track of all this crap up here. And I'm going to be honest with you. The hard part with this problem was setting the tree diagram up. That you did something in stages, or you did something in steps, more than one step there. Now, the problem I gave you for homework, just like that. Obviously, it's not cancer and test. Okay? There's a part A and there's a part B. You're going to make the tree diagram and you're going to answer some question where you're going to have to add 2 of them up that have whatever you're looking for. Like here it was a positive test, so I took present and positive, absent and positive, added those 2 probabilities together and got that 0.06, what is it? 0.06945. How likely is it that the test comes back positive? It's more likely the test comes back negative, isn't it? 7% of the time the test comes back positive, yeah? Everybody understand why I'm saying 7? Okay, 6.9% of the time the test comes back positive, irregardless of the cancer being there or not. What probability does it come back negative with? Well, take 1 minus 0.069. You know, like 93.1% of the time the test comes back negative. Which is more likely to happen? The test comes back positive or the test comes back negative? It's way more likely to happen that the test comes back negative. Now, I can't let this problem go. I got to do one more piece here. There's problem 1315. Continue your work from exercise 1313, this guy right here. The probabilities given in Table A of exercise 1313 are properties of the PSA test. The false positive test is a property of the PSA test as applied to a population. Part A says, suppose that 6.3% of the population has prostate cancer. Not a large group of people, right? What is the probability that a person that does not have cancer, given that the prostate test is positive? Okay, so I'm going to write it down like this. 1315 is asking me this. What's the probability that cancer is absent, given that you have a right? So it's a given that. I mean, that's a conditional probability like I was talking to you out of the 2-way tables. They want to know what's the probability that the person does not have the cancer, right, that it's absent, given that the test comes back positive. This is a false positive, right? The test comes back and says, yes, you do, but actually you don't. These are false positives. Now, I'm going to make this real short and sweet. You're not looking at every test. You're only looking at the ones that are positive, yes? So the number that goes in the denominator here, and I know when I did the 2-way table, I had numbers I put in there. Here I'm going to use the probabilities on you. I'm going to put this probability here, 0.06945. That was the probability of a positive test, and that's what goes in. Rob. Rob?
Yes, sir.
You still there?
Can you not hear us?
I can hear you. Can you see me?
I can see you.
Can you hear me?
Yes, sir.
Can you see the shit I'm writing on the thing?
Can y'all see that? Yeah. Yes, sir.
Yeah. All right, we're good to go because I can't see you folks, but that don't matter. So when I got this conditional probability, and I don't have counts here, I got probabilities. The part, given that part, that probability goes in your denominator. The probability that goes in the numerator, since you're not looking at both, you're not looking at everything, you're just looking at those two, this is going to be this 0.05622. Now, if you'll notice what that is, that's the probability of absent, and it was a positive test. That's what goes in the numerator there. That it's a absent, and the test is positive. It's just that one piece out of your tree diagram. You punch this in the calculator, and what do we get here? 0.81. 81% of the tests are false positive tests. You know how many men you've upset with this? Oh, shit. 81% of the ones you test come back false positive. Let's say we tested all men. This is off the top of my head. I got 7% of the tests are going back positive. How many men are we looking at in the country? 50 million to be conservative? What's 7% of 50 million? That's a big-ass number, ain't it? That many come back as positive. Take 81% of that number. You're still looking at a big-ass number. Those are the ones that came back false positive. You understand why we don't mandatory test for prostate cancer? You got a whole bunch of pissed off men. You understand? Look, the same kind of thing works here. I mean, this is about prostate cancer. The same kind of thing works here when you start doing, like you're testing for something that's rare in the population. When something happens 6.3% of the time, that's rather rare, right? You know, if you start testing for AIDS, that was rare in the population, right? Well, it turns out most of the positive tests come back as false positive tests. Actually, in my old book, that was the example I had. They did the test for AIDS. It turned out like 67 or 68% or 69% of the tests for AIDS come back as false positives. And then people want to know why we didn't test everybody for it. Okay, we'll take everybody, 300 million. The probability that the test come back positive was close to like 7 or 8%. Look at 7 or 8% of 400 million. Take 70% of that, you got a bunch of pissed off people. And then so one semester, I was actually talking about in that class. I had a little girl in the back of the room. I probably shouldn't keep telling this story. I didn't give her name, right? I had this little girl in the back of the room. She's like, I've been tested. At that point, you don't want to ask. Right? She said, yeah, I was tested. And I'm backing up. I don't want to ask. I'm trying to. She said, yeah, I tested positive. And I'm like, really? I don't really ask now. I said, well, what'd they tell you? Oh, I'll come back next week. We'll test you again. Hell, you're probably a false positive. Then I got away from that question. And I didn't ask her what happened the next week. And it's because of this same setup here, right? You know, come back next week. Hell, we'll test you again. Now, if you test this time, then we got a problem, right? 2 false positives in a row probably don't happen. But 1, well, hell, it's a high percentage that are false positives. Yeah. Okay. Now, the problem I gave you about a tree diagram is I think I gave you problem 1353. The tree diagram's already drawn out for you because that's the hard part that I think about there for you. It's in figure 13. I'm on page 324. 1353 is about fundraising by telephone. Okay. Instead of being 2 steps, there's 3. Right? The tree diagram's on the bottom of the page. So you don't have to draw a tree diagram for me. Right? It's there. I know you can see it. And then you just answer the 2 questions. Now, warning. Part A, that's like 1313 question I asked. And part B is like 1315 question I asked. It's a given that question. Okay? Now, what I want to do for the next 10 minutes is I want to get us started on the next chapter. I know the next chapter is supposed to be 14. I know 14 is listed on your syllabus. I know 14 is listed in Learning Curve and all that crap. I'm not assigning 14. If you looked at Learning Curve, I went from 13 to 15. We ain't going to do 14. We don't need it. It's optional, and I'm making it the option. We're not going to do it this semester. It's not going to have anything to do with what we're going to do from here on out. We used to stop off and do it when we had some extra time, but they added shit at the end here, so we're not going to do it. There'll be no questions on your final about it. There'll be no learning curve. I know it counts 2.5 points. Everybody starts with 2.5. Since I didn't assign that one, no big deal. I take care of all that. All right? Everybody clear, right? Nothing out of chapter 14. Now, we go to chapter 15. And I'm going to be honest with you. Chapter 15 is a big deal. All right? The chapter 15, the title of it is Sampling Distributions. Now, you're supposed to know at this point what a distribution is, right? It's usually the distribution of a variable. Hell, last Tuesday we had probability distribution of a random variable. Whatever I'm talking to you about when I'm talking to you about a distribution is, I tell you two things. I tell you what value the variable takes, and I tell you how often it takes them, whether we're talking about probability or whatever. Well, then they throw a word sampling in there. So there must be something special about this sampling that they stick it with distributions. Now, here's the way this first part works. We won't get to talk about sampling distribution until Tuesday, all right? But if you'll take a look here, and I'm on page 345, and it says how much, I'm assuming it's the same question as always. How much on the average do American households earn? So we've had our probability taste. Now we're back to statistics. All right? Here's my thing. You understand when I'm looking at all American households, that's your population, right? And what I want to know is what's the average household income for all American households? I mean, we're looking at over 100 million. Are we going to call them all? Your population's too big here, right? You don't have enough time or you don't have enough money to talk to every household. So what does somebody have to do? That is a question about a population that is large. I am back to chapter 8. Okay? So somebody takes a sample, and it says, the current population survey asked this for a sample. And you had a sample, and at this point, we always want to know our sample size. Remember, I told you we use N, and they sampled 98,095 households. 98,095 households. I mean, that seems like a large sample. Not when you're looking at 100 million households, 98,000 ain't that large. Okay? And what they did is, they actually asked them, what was the household income for the year? They found an average. They found X bar is 71,274. And I always ask students, don't that seem high? It's the mean, though, right? What do we expect about the mean here? We expect the mean to be pulled out the tail because I expect these incomes to be skewed to the right. The book tells you that the median income was, of course, lower at 51,017. That sounds a little better, 51,000. There's your mean. Now, I'm going to change colors on you. This right here is about the sample. How do I know that? It was calculated from your sample. Okay? We want to use it. You see that number there? I want to use this 71,274 based off of this sample of 98,095 households to estimate. You remember my little picture I keep drawing? I want to use this, and I want to say something about the question about the population. I want to say something about the average household income for all American households. That's inference. Taking what you learned from your sample and inferring back to about your population. Okay? Now, when we do that little move, I always think about sample. This is just me. Infer to your population. Now, this little story here, that we're actually going to start doing that, taking what we've learned from the sample to infer back about the population, that's the next chapter. This is the chapter to get us started to be able to do that. All right? Now, I'm going to make this real simple. We're all about random samples, whether it's an SRS, stratified, systematic, multi-states. I want to see a random sample, right? So then I would expect my sample to be representative of the population. Yeah. We're all about, I'm thinking about the ways we produce data. When we did an experiment, it's always randomized comparative, right? It's the way we produce the data. It uses chance. So our problem is, whether it's a sample, a random sample, whether it's a randomized comparative experiment, we always use chance. You do understand that we produce data using chance. That's the right way to do it. Right? But when we do this, we cannot guarantee our results of inference. This idea of inferring back. Since we use chance, we might be completely wrong. Right? We use chance in randomized comparative experiment, random samples. We cannot guarantee our results of inference are correct. All right? So, with that said, we can. I'm getting to the point where students start saying, really, dude, you said that? You want to do all this shit and I can't guarantee our results? Yeah. But what we can guarantee that our methods usually give correct results. Look, this is the language that I have here. And what I mean is the methods we're going to have two, and we're going to repeat them from chapter to chapter. We're going to give you how often they are successful. We're going to attach a probability to them and tell you, look, 95% of the time we're correct. I can't tell you whether the one you're looking at is correct or not. That's what we mean we can't guarantee our results for inference. But I can tell you about our method that we're using. I can tell you how often it is correct, right, if I used it over and over again. Because that's the way inference works. That's the way all this works. This is the reason why probability back in chapter 12 was defined the way it was. Remember, it's the number of times, the proportion of times your outcome would show up if you did it over and over again. It plays right into inference, this idea of the reasoning of statistical inference. What would happen if I used this method over and over again? Well, then I can give you a probability of how often it is correct. I'll give you a probability of how successful it is. That's what we'll do. Now, I'm not done talking to you about that one ever. We're going to talk about that again when I start the next chapter. But we need a couple. Look, I know I got 6:48 here. I need two definitions before we get to going on this kind of stuff. I need parameter, and I need statistic. These are on page 346. See, from now on out, the rest of the semester, there's two groups of individuals, your population and your sample. There's something you want to know about your population, and there's something we calculate from our sample, so we need language here. So when I think about parameter, this is usually an unknown quantity about a population. So we always speak of a population parameter. It's an unknown, like I said, it's usually an unknown quantity that's dealing with your population. And then the statistic is calculated from the sample. So you'll hear me speak of population parameters, some unknown quantity about some large group population, and you'll hear me talk about a sample statistic. It's something that's calculated from your sample that you took. We'll pick up there on Tuesday because I'm out of time, but the statistic's always about your sample. It's calculated from your sample. The parameter is always about your population, and for us, it's usually an unknown quantity. All right? Make sure you get your homeworks back. Rob, I sent them back to you. I emailed them back. We're good. Okay.
They were not in my box, Mike.
What?
I didn't have any homework.
You ain't got no test?
I have the test. I don't have the.
No, man. There was 3. There should have been 3.
Okay, well, I'll find it and give it back on Tuesday.
It was their homework. It's the quizzes for calculus, and it's the calculus test.
I have the quizzes and the test, but I didn't see the third package.
Should have been a third one there.
All right.
The graded one's back.
Yeah. I mean, he emailed me a picture of it, and I was like,
I guess a couple of those.
there's one that I was
If you have today, I'll throw it into it.
It's like I missed a class. That's the best.
What year are you?
I'm sorry?
You get it down one day, bro.
Yeah.
You gotta do your homework on the Right.
Yeah, I passed around a little earlier.
How was that on?
sorry.
And she comes the lowest forward, and they're all that day that he passed them out.
I didn't bring it.
What's that?
You don't know what, do you know what you made? Dad?
Did you sign it as well? You did sign it.
So
Do you know Shane or Adrian Hutton? Shane,
I am minor now, but I'm doing, like, I decided to do
B-E-K-E-R.
B-K-E-R. I know, I almost was like, she's still teaching it in the spring.
Oh, she's still teaching this morning.
Yeah, she's teaching the lab and she teaches like now they quit.
I think they switched in the spring for like. So I assume he might. Are you sure?
I don't know, but her name's on it for lecture and lab. So. Well, sometimes he teaches in college, right? Maybe. I've heard, don't do it because I've heard that if you get the guy that is different, you can take a look and get full.